Okay, students, so we are back again for the next session. And in the morning I highlighted an important equation, and that is RT XA ln gamma A plus XB ln gamma B is equal to G X mixing, which is essentially the non-ideal mixing. And we talked about that we can express GXS mixing in different ways. Actually, it's not arbitrary. Normally, these are done experimentally by drop calorimetric methods. There are several methods by which we can determine the amount of energy that is exchanged on mixing in different compositions, and from there we can subtract the ideal mixing composition, and what we are left with is the excess mixing composition. So those can be theoretically determined. So once they're theoretically determined, then we have to do an essentially curve fitting to it to find out how the equation is changing as a function of composition and temperature. This is a very standard way of doing things. But a very simple way of doing it is considering its WAB, XA, XB. That's a very simple way of doing it. This is called a Margol's parameter, and this is called regular solution behavior, where mixing is 0 at A is equal to 1 or B is equal to 1, that means at the end members, and the maximum of value occurs at XA is equal to XB is equal to 0.5, and that is where the maximum value occurs, or the curve is symmetric on either side of XA is equal to XB is equal to 0.5. Now, I have sent you 2 PDFs last week. One was on thermodynamics of crystalline solution, thermodynamics of pure phases, and the other one, the second one, was thermodynamics of crystal systems, thermodynamics of solid solutions. I hope you have gone through it. You have to go through it. But in that case, the derivation, that means this derivation, XA ln gamma A plus XB ln gamma B is equal to WAB by RT into XA into XB. This equation is solved to find out RT ln gamma A and RT ln gamma B. This we have found. I derived these expressions. And this comes out to be WAB XB squared, and this is WAB XA squared. It turns out to be. These are the 2 end members of what it turns out to be. RT ln gamma A is equal to WAB into XB squared, and RT ln gamma B is equal to WAB into XA squared. This is how it comes down to if you make the derivations, which is essentially from Chatterjee's derivation. Now, you might be wondering, okay, so we have done a little bit of thermodynamics of crystalline solutions, and I have showed you the thermodynamics of pure phases. What are we going to do now? I'm going to show you how element partitioning occurs and how it can be treated thermodynamically. Have you understood? I will talk to you a little bit about this. How element partitioning can be modeled using the thermodynamic equations that are studied. Once we have done that, we will talk about the thermodynamics of orthopyroxene that we started with. That we will do just a bit later. But for the moment, we will try to find out how does the thermodynamics of element partitioning essentially work. So remember the equation. This is a small board, and I've got to always be very careful So let's say we take a reaction like this. You may be knowing it, or your teachers may have told you in the masters. Something like, say for example, Mg Fe exchange. Mg Fe exchange, we can take an arbitrary one between, say, biotite and garnet. Let's say biotite and garnet. How does this work? That's what we're trying to look at. Now you must understand here, biotite is a phase. It's a mineral phase. It's a thermodynamic phase. Garnet is a thermodynamic phase. So we have identified two phases, but we have not identified the phase components of each of these phases, biotite and garnet. Normally, biotite and garnet, they are multi-component systems, where the thermodynamics have been done by several very famous people. They have done it, but we would try to keep things simple. We would like to see always the logic, not to make the equations very colorful and very big, but you don't see through the equation into the logic. I want you to understand the logic of it. Equations can be made complicated. Equations can become complicated, but that's not the issue. We've got to know how things are working. For that, we can take a simple binary model for biotite and a binary model for garnet. So for doing that, we take surface biotite. The formula is K Mg3 Al Si3 O10 OH whole twice. This is one component of biotite, and as you know, the name is phlorbite. The name is phlorbite. But if we take the iron member, because it talks about magnesium iron exchange, then we have Al Si3 O10 OH whole twice. So these are the two phase components of biotite, and we are trying to understand the Mg-Fe exchange between biotite and garnet. So if there is to be magnesium and iron exchange between biotite, then of course we have to take at least magnesium iron exchange in garnet. So for garnet, for example, we can take two components, say Mg3 Al2 Si3 O12 and Fe3 Al2 Si3 O12. Let's say we take this composition. So garnet is a binary solid solution of magnesium and iron, that is pyro and aluminum, and biotite is a binary solid solution between magnesium and iron, both in the octahedral site. Here the mixing is occurring in three sites. Here the mixing is occurring in three sites. It could have been in two sites as well. It could have been in one site as well. But the important point here is that it's occurring on octahedral sites, 3 octahedral sites in garnet and 3 octahedral sites in biotite. And so for biotite, Fe biotite is equal to amount of Fe by Fe plus Mg in biotite octahedral site, and for iron, Fe garnet is equal to Fe divided by Fe plus Mg. Have you understood? Right. Now with this, we start to write. So if you have FeFg exchange between biotite and garnet, then you have to write a stoichiometric reaction of magnesium and exchanging between biotite and garnet. Now, we can write a reaction of this type. Say, KFe3 Al Si3 O10 OH4 twice plus Mg3Al2 Si3O12. Have you understood? Is equal to K Mg3Al Si3O10 OH whole twice plus Fe3Al2 Si3O12. Have you understood? So here you see the iron in the biotite, and this is magnesium in biotite, this is magnesium in garnet, this is iron in garnet. So you can see this iron goes into garnet and this magnesium of biotite goes into garnet. So essentially the phases, mark my words, the phases. Here the phase is biotite and garnet. In equal to sign, the phase is biotite and garnet. But the phase components are interchanged. So this is called an exchange reaction. And you will see they are all balanced. All balanced. Here you see 3 iron, 3 magnesium, 1 potassium, 3 silicon, plus 3 silicon, 6 silicon. Here it's 3 silicon, plus 3 silicon, 6 silicon. If you take oxygen, here you will see oxygen is 2 plus 10, 12, plus 12, 24. Here you will see 2 plus 10, 12, plus 12, 24. So all elements are balanced. All elements are conserved within the reaction. Now, if there are 3 sites here, isn't it, in biotite? And there are 3 sites in garnet. Remember, in orthopyroxene, magnesium and iron that we were doing, they were partitioning between M1 and M2, both octahedral phases. But yet there was a size difference. Here, we consider, for simplicity, that all the 3 sites in biotite were mixing occurs, and all the 3 sites in which mixing occurs between magnesium and iron in garnet, they are same. So the 3 octahedral positions have the same characteristics. So there is no partitioning, size-based partitioning of the elements into the site, because all 3 sites are essentially the same. So if we do this, then you must have, if you have read my PDFs, there has to be 3 equations. So for writing for chemical reaction, you have to write equations of state. Equations of state. So for example, you will have 4 such, because there are 4 components, 1, 2, 3, 4. There are 4 components. So for 4 phase components, you will have 4 thermodynamic equations of state. So, say for example, let's take this biotite. And we take magnesium biotite. If I had to write an equation of state, we write G phlogopite in biotite, remember? And we write G phlogopite 0 biotite. Remember, there is also pressure and temperature here, because thermodynamic equations state are equations of state. So they have pressure and temperature, plus RTLN, activity of phlogopite in biotite. Activity of phlogopite in biotite. Have you understood this? Right. But remember again, this is the energy of impurity. This is the energy of purity. Right? Now, from the appendix, we can simplify this G0. Remember, G0 value is for the pure phase, so it's not composition dependent at all. So they are functions of pressure and temperature. And you must have heard they have something called, I have talked about heat capacity equations. So there are isothermal heat capacity equations, there are thermal expansion data. All these are shown there, the derivations are given. But we take things very simply. We write G0 as a very simplified equation, where you write H0 phlogopite in biotite minus TS0 biotite phlogopite plus P into V phlogopite into biotite plus RTLN activity of phlogopite in biotite. This is the equation for G phlogopite. Have you understood? So there will be, this is phlogopite. So there will be a phlogopite as written in this equation, as shown in this equation. The right hand side forms the product, and the left hand side forms the reactant. But it is equal to sign. If you took it the opposite way, nothing would happen. Only the signs would change. So it does not depend how you write. It depends on that you write a stoichiometric equation, balanced stoichiometric equation. So I have written for phlogopite. So there will be another equation for almandine, a very similar equation for almandine, and we can write this is not right, phlogopite and biotite. Then we write almandine in garnet is equal to H almandine in garnet, 0, minus T S almandine in garnet, again 0, plus P into V almandine garnet plus RTLN activity of almandine in garnet. So for each phase of bond there is a reaction. So there will be one more reaction for anite, there will be one more reaction for anite, and there will be one more reaction for phlogopite, for pyro. So there will be 4 more equations of state. So there will be 4 more equations of state. Now what happens at equilibrium? At equilibrium, the free energy of the products is equal to the free energy of the reactants. Have you understood? The free energy of the products is equal to the free energy of the reactants. Or, okay, let me write that. So G of product is equal to G of reactant. Is it alright? That means delta GR, that means the free energy change of the reaction, at a particular pressure temperature condition is equal to G product minus G reactant. And at equilibrium, this value is equal to 0. At equilibrium PT condition, G product is equal to G reactant. Now del GR, that is the free energy change of the reaction, is equal to G product minus G reactant. So this will be equal to 0. So here you can see, I will erase this. Delta G of the reaction is equal to 0 at an equilibrium PT means G of phlogopite in biotite plus G of almandine in garnet minus G of anite in biotite plus G of pyro in garnet. This is equal to 0. Right? So now, those 4 equations of state, instead of G phlogopipe, I can then write G0 phlogopipe, etc., etc., etc. That means I can write now del H0 of the reaction minus P del S R0 of the reaction. Remember, this is for the pure phase, nothing to do with standard state. Plus P delta VR0 of the reaction plus the RT ln A term. So then we write plus RT ln, now will come top, will come the product. So activity of phlogopite in biotite into activity of almandine in garnet divided by activity of anite in biotite, activity of pyro in garnet. This will be the expression, equation of state for the reaction. Now, I can ask you, what does del H0R mean? Del H0R mean? It is the product minus the reactant. So what is del H0R? It is H0 phlogopite plus H0 almandine minus within bracket H0 anite plus H0 pyro. That is what it is. Same with entropy, same with volume. Same with entropy, same with volume. Now, having done this now, we write this del HR0 minus T del SR0 plus P into del VR0 plus RT. Now you see the mixing, normally the activity of a site is given as X into gamma into the power n divided by to the power n. What is this n? N is the number of sites. N is the stoichiometric coefficient, which is 1 in all cases. Have you understood? Have you understood? So what is important is activity is equal to X into gamma to the power n to the power n. There is a theorem for this. There is a derivation for this. That means, what is n? The number of sites on which mixing occurs, which is 3. And what is m? Is the stoichiometric coefficient of that particular phase component. Here, the stoichiometric coefficient is 1. So having written this, I can write plus. Now you see, X phlogopite into gamma phlogopite whole cubed, activity of almandine into gamma almandine cubed divided by X anite into gamma anite whole cubed into X pyro into gamma pyro to the power 3. Why not to the power 3 to the power 1? But the stoichiometric coefficient is 1 in all cases. Now, let us go to the next point. I don't know how to manage this space. it is very difficult for me. But anyway, I have to keep on working on it. So now we have 0 is equal to del H R 0 minus T del S R 0 plus P into del V R 0 plus 3 RT ln. Oh, sorry, I have forgotten. There should have been an RT here. Should be, I'm sorry for this. 3 RT ln, because it's the RT ln activity. Okay, so it will be how? 3 RT ln x mg by x fe biotite into x mg by x fe garnet plus 3 RT ln gamma mg by gamma fe biotite into gamma, no, what was the equation? Gamma mg by gamma fe biotite, sorry, this should be reversed. Into gamma fe by gamma mg garnet. Now you can see this equation. This part is composition independent. Composition independent. This is only based on pressure, temperature, relation. These two terms are based on compositions. Both the mole fraction and the activity coefficients are based on composition. This will lead us to a very interesting relation. We will look into it. 0 is equal to del HR 0 minus T del SR 0 plus P into delta VR 0 plus 3 RT ln xmg by xfe biotite divided by xmg by xfe garnet. You see that? I have divided this, so this is reversed. Plus, it's the same. 3 RT ln and this. So it will be gamma mg by gamma fe in biotite divided by gamma mg by gamma fe garnet. Have you understood? This is where we come to. Now this is interesting. You must understand now. In this equation, this is for the pure phases, dependent on pressure, temperature. This part, where there is no gamma, it deals with ideal solution energy parameters. Have you understood? Remember, here it is the ideal solution parameters. And this part accounts for the non-ideal. So this is for pure components dependent on pressure and temperature. This is the energy term for ideal mixing in the reactor. Effects of ideal mixing on the reaction. And this effect is the effect of non-ideal energy changes in the reaction. So these are the three parts in the reaction. For the moment, I will not consider this at the moment. I will come back to this later. You please remember the reaction. You will forget. So it is like this 3RT ln gamma Ng by Fe. I will write it somewhere because I don't have anything to write on. So I will write it as, I will write it on. Because if it goes into the next class, I will have difficulty in coming back. Right. So if we are not taking this term, that means we are neglecting the energy changes due to non-ideality. Let us do that as a first approximation. I am not ignoring what I am saying. I will keep it at abeyance. Let it hold for some time. I will be coming back to that. Let us see beforehand. So, I will erase this part. Have you understood? So that this part does not appear. It will also help us to see the equation a bit better. Remember, this is the ideal mixing component, ideal mixing energy due to ideal mixing in the reaction, and this one which I have erased off is the effect of non-ideality in the exchange reaction thermodynamics, which we have kept it in abeyance. Now here there is something very, very interesting for me, and this is the central theme of thermodynamics of element partition. No matter what the phases are, no matter what the phase components are, the equations don't change. The values change, the theory does not change. Now this is interesting. Okay. I will try to manipulate this a bit. So I will write xmg by xfe biotite divided by xmg by xfe garnet is equal to, I will give you a little time, exponential minus 1 by 3RT into del H R0 minus T del S R0 plus P del VR0. What I have done, I have taken this to the left hand side, so this remains positive. Then I divided it by 3RT ln, 3RT, and took the exponential of it. So this is how the expression looks like now at the moment. Think about it. I have taken this equation to the left hand side. Then this right hand side I have divided by minus 3RT. But I have a ln here, so I took the exponential, and this is what the equation is arrived at. Have you understood? This is what I arrived at. Now, this is interesting. Let us look at this value, del VR. What is delta VR? 0 is equal to volume of phlogopite plus volume of almandine minus volume of anite plus volume of pyro. This is what it means, delta V means. Now, if I interchange this value a bit, then you have V phlebobyte, V0, minus V0 anite, minus V anite, 0, minus V, no. This is how the equation will be. V phlebobyte minus V anite, right? And then I write minus. The moment I write minus, V pyrope has to come here. And then minus of minus, it's V alum. So what is happening here now? Now you see. If you remember, magnesium ionic radius is 0.66 and iron ionic radius is 0.74. Okay? So if we take this to the molar volume, then this term, volume of anite, should be slightly higher, which is efficient, slightly higher than the volume of phlebobyte. Then this term is small negative. Yes or no? Volume of phlebobyte, this is small, minus volume of anite, this is larger. So if you take the difference, this will be a small negative value. And what about this? Again the same thing you see. Magnesium 0.66 minus V0 aluminium, which is slightly of a higher molar volume. And so this value will be a small negative value. So a small negative value minus a small negative value, this value should be small, very small. So delta VR0 of the reaction should contribute very small to the energetics of the reaction. Tell me how you understand. What I am trying to emphasize here, the effect of this term, d delta V0, is very small because of this relationship that you have a small negative term being subtracted from another small negative term. And so the net effect del VR is very small. So unless you multiply it with a very large pressure value, P del V0R should be a small contributor to the energetics of the reaction. So if pressure is very high, then you can multiply it into a smaller number and you get a substantially big value. But if your pressure is small, then of course the effect of this value is very small. So for our discussion, what we do is, we understand that this term has a small effect on the energetics of this reaction. If it is so, then you can see, if you ignore this term, for example, you will see that your expression now, the ratios of this at a particular temperature and say a pressure, this is a constant. Have you understood? The right hand side of the reaction for a particular temperature within bracket and the pressure, knowing that pressure is affecting it very small, largely the effect is because of the high temperature of the temperature. So this term on the right hand side is a constant. This means if this is constant, then this ratio is constant. This ratio, this at a particular pressure temperature, if this is constant, that means this ratio, mind the word, ratio is constant. So I can write xmg by xfe biotite divided by is equal to XMG by XFE garnet into a constant at AP. This, if I see, at a particular T value, if I get this term, then this is equal to Y is equal to X into M, this value is M, plus C is equal to 0. So this is the equation of a straight line passing through the origin. So if I plot what is my X, Mg by Fe, XFE garnet, and here you have XMG by XFE biotite, then at a particular temperature, the ratio will lie on a particular line. Have you understood? They can have different values. These values could be different, but the ratio will be the same. Have you understood? That the values individually could be different, but the ratios have to lie on this line. But if, say for example, you change the value of that, no, that is why this is called an equilibrium constant. Equilibrium constant. Because at a particular equilibrium, this value is a constant. But if you change the temperature value, then this remains a constant but a different value. Have you understood? It will again have a numerical constant value, but that value will be different from the other T that you took. So you can conceive that you will have numerous reactions for a particular temperature T1, T2, T3, T4 and so on. So if you take T1, then all your plots should lie. If you plot XMG by XFE garnet versus XMG by XFE biotite, it should lie on this line. But it could lie everywhere. So you can have a point here, you can have a point here, you can have a point here. But the important point is they will have the same slope. Have you understood? But if the temperature was T4, then for the same composition of MgFe biotite, this should be MgFe biotite for the same set. Have you understood? So for this point, this will be the set. For this point, this will be the set. Have you understood it? So that is a very important point that I am trying to mention. So for see, if I take this XMG value, XMG by XFE garnet value, if this is the temperature, this will be the Mg by Fe ratio in biotite. But at temperature T4, this will be the value of Mg by Fe biotite. So what it is doing is, if the Mg by Fe values of the biotite is changing, or if you take a particular value, same thing for a garnet, that means the change of Mg by Fe ratio or the composition of Mg by Fe in the sites, therefore, is a function of pressure and temperature. Is a function of pressure and temperature. Have you understood it? This is the very, very important aspect. That temperature and pressure, I'm not showing you in this equation because the volume change is very small. So the temperature and pressure determines, say for you have a pyroxene or a garnet, what will be the composition of that biotite and garnet? That would depend on the pressure temperature condition prevailing at that time. If you change the pressure temperature condition, the ratios of the compositions will also change. Will definitely change. So this is what I have done by considering ideal mixing. Remember, this is all for ideal mixing because I have ignored the non-ideality. Have you understood? I have ignored the non-ideality. So once again, this is one thing that is important. Tomorrow I will want to go into next class when I will take you to non-ideal components, non-ideal exchange, etc. So in this case, where this condition, I have neglected gamma terms. The gamma terms were, if I can tell you again, gamma terms were RT ln gamma mg by gamma Fe in biotite divided by gamma mg by gamma Fe garnet, this term. I have neglected this term. It means either the individual gamma values are 1. Have you understood? Individually, the gamma values are 1. What does this mean? If gamma mg and gamma Fe for biotite is independently 1 means what? Mg Fe is an ideal solution. Similarly, gamma mg and gamma Fe in garnet is individually equal to 1. That means you are dealing with an ideal, completely solid solution which is ideal in nature. But it could so happen that they are not individually 1, but they mutually cancel out. They are not individually 1, but they mutually cancel out. So individually, none of them are non-ideal solutions. Not ideal solutions. They are non-ideal solutions. But the non-ideality may cancel out. In which case, the solutions are not ideal, but it is an ideal exchange. Have you got my point? When gamma values are independently 1, that means solid solution of Mg and Fe in biotite is ideal, and solid solution between Mg and Fe in garnet is ideal. But if it is non-ideal, you can still have this value neglected for the child if these two ratios cancel each other out. That means this is individually non-ideal, this is individually non-ideal, but their non-ideality cancels each other out. Then it is not for ideal solution, it is an ideal exchange. Both cases, the effective reaction would be this. The effective reaction would be this. And this is what will follow. Okay, thank you. We will continue in the next class on this discussion.